right, so we're recording. So yesterday we got a little bit late start because of WebEx issues. But one thing we did accomplish yesterday is we went through and worked an example where we used method of sections to cut a member at a particular cross section and determine what the internal loads were acting on that cross section. Those internal loads being a normal force that's perpendicular to the cross section, shear force that's tangent to the cross section, and a bending moment. So before we go any further, again, if anybody has any questions about that process of finding internal loads, we'll take a minute or so, however long we need, clear up any questions about that. Hopefully, maybe you started working on some of those suggested problems out of the textbook on that first section. And not seeing any questions. Not hearing anything again. Maybe I should do what I did yesterday. I reckon this time AJ Patel is on top of my list. So AJ, if you would unmute and say something, just let me know you're out there.
Can you hear me?
I can hear you fine. Can you hear me?
Yes, sir.
Okay. I just wanted to make sure that I had a live person out there. You can go back to mute, but again, anybody, if you got a question, don't hesitate. Chime in. All right, so what we're going to talk about today, first thing is we're going to define what stress is. And we're going to be doing stress, the mechanics materials definition of stress, not the stress caused by the coronavirus. This is in section 1.3 in your textbook. And first, just kind of a real general definition when we refer to stress in mechanics of materials, we're talking about force per unit area. So it's a force acting over an area. It might sound very similar to pressure, and in a way it kind of is. And we're going to define two particular kinds of stresses. First, what we call normal stress. And what we're going to see from as far as the effect on the material, stress is going to determine, again, how much that material is going to deform. Is it going to break or not? And for normal stress, notation-wise, we're going to use, my sigma is probably not real good, but this is a lowercase Greek letter sigma. If I can't. My sigmas may not look super great. You can look in the textbook and see one, but what it is it's a lowercase Greek letter sigma. And one of the things you're going to find, at least I've been told, a challenge for a lot of students for this class is just being familiar with the terminology and the notation used. It's almost like learning a foreign language, if you will. You got to know what all these Greek letters represent and understand if you want to excel in mechanics of materials. So what the normal stress is, this is the normal, or the force that's perpendicular to the surface area per unit area. So kind of related to what we were discussing yesterday, if you're looking at some arbitrary cross section like this, right? So if you had a member and you went out there at some location and you cut it, and you looked at that cross-sectional area, then the normal stress is the stress caused by this force that is perpendicular. Let's see if I can. That's not a real good straight line. Again, if you remember the notation we used yesterday, we call that internal loading. That was force that was perpendicular, was used N. And so that's what the normal stress would be. It would be the stress caused by this normal force, the force that's perpendicular to the cross section. Whereas what we call shear stress again, notation wise, another Greek letter. This is tau. It's a lowercase Greek letter tau. And this would be the stress due to the force that's tangent or parallel to the cross-sectional area. So it would be the force that's tangent to the surface per unit area. So using a similar illustration here, we're looking at this arbitrary cross section, some area A. Shear stress would be due to the force that's tangent or parallel to that surface, which notation wise yesterday we call that V for the shear force. It's the force that's parallel to that surface. Now in general, stress is going to have units. Not real hard to figure this one out. Force per area. So some unit of force divided by area. Some examples commonly seen. If we're doing English units, maybe the force is in pounds. Area, more often than not, probably would be in inches squared. Now, there's nothing wrong with writing it like this, pounds over inches squared, but it's much more common to write it like this, PSI, pounds per square inch. And so this is a notation that you're going to see in the book. This is the notation that I'll use. Those of you who had me before know I'm picky about units. And so if you're working a problem, you got to have units on your answers. Now, which way you write it, I won't be picky about that. I won't count off if you write it as pounds over inches squared. But just be aware, the 99% of the engineering world out there is going to write it as PSI. Another example involving English units, if the force is, instead of pounds, could be in kips. And again, English units, the area is almost always going to be in inches squared. And I found when I teach this course that it seems like there's always at least one person in mechanics materials that does not know what a kip is. So I'm going to go on that same assumption that there's at least one of you that is not familiar with the the notation of the term kip. It's English unit of force, but it's using SI notation. So it's kip is short for kilopound. That's what kip stands for. It stands for kilopound. So 1 kip is equal to 1,000 pounds. Kind of like a kilonewton is 1,000 newtons, a kilopound is 1,000 pounds. So if you're dealing with really large forces, you might see this term used. just like PSI, if our force is in kips and our area is in inches squared, typically it's very common to write this as KSI instead of PSI. That's indicating it's kilopounds per square inch. So one KSI would be the same thing as 1,000 PSI. But if you're dealing, again, with really large numbers, that might be the motivation for using KSI instead of PSI. If we're dealing with SI units, metric units, the unit of force probably is going to be in newtons. And most commonly, the area would be in meters squared. And again, there's nothing wrong with that notation, but that's not what is commonly used. This is given a name. It's called a Pascal. So rather than given the notation as newtons per meter squared, it's very common to write it as a Pascal. Now, if you're calculating stresses with SI units, typically these stresses are going to come out to be very, very large numbers. And so it's very common if you've got something, say, in the millions of pascals, to write it using megapascals. So again, this would be a megapascal. And if you're not familiar with those SI abbreviations, mega is 10 to the 6th. So this would be the equivalent of 10 to the 6th pascals. So very, very common. If you're calculating stresses in SI units, you're going to get really big numbers, and so your answer or stress typically is going to be given as so many megapascals. And you just need to be familiar and know that, again, mega is 10 to the 6. All right, any questions about just the basic definitions of stress or the units, the notation? I'm not seeing or hearing anything, so we will move on. Now, I mentioned, I think it may have been Monday, I don't know, all these days start running together, that we were going to look at the effects that these 4 internal loads, now the one we haven't talked about or done anything with yet was the twisting moment or the torsion. Again, we just dealt with normal force, shear force, and bending moment yesterday. But I mentioned, I think Monday, that what we're going to do is essentially look at what each one of those does individually. And then later we'll combine them. And so what we're going to do first is look at normal stress due to this normal or perpendicular internal force and calculate, again, what stress it causes. And then maybe tomorrow we'll should get into looking at shear stress due to that tangent or shear force. So first up, again, would be what's in the next section in your book is section 1.4. And we're looking at normal stress in an axially loaded member. Again, we're really limiting, what kind of situation we're looking at here. We're limiting to something like this, where you've got a bar, and the only load applied is going to be this axial load we'll call P, right? So that's it. That's all. We're going to limit ourselves to just looking at this situation. Again, as we get further, it's going to get more complicated. But now there's two possibilities. It could be loaded like this, which is what we would refer to as tension. Or the forces could be in the opposite direction, and that would be an example of what we call compression. Again, this would be what we refer to, if I can spell it, compression. Right? That's it. That's all we're considering at this point is some member loaded with just an axial load. Now, there's two big assumptions we're going to make at this point. One is, come on, focus for me. I don't want to focus. There we go. So first assumption is that the bar is straight. So it is, I spelled that right. It's not curved or bent. The bar is going to be straight. And also that the axial force acts along the centroidal axis. And what I mean by the centroidal axis is if you look at the cross section, it's this longitudinal axis that would run along the axis that passes through the centroid of that cross section. Right? So that's what we're referring to. The centroidal axis is this axial load has got to be applied along that axis. Now, the result of this, maybe I'll ask a question. We'll see if anybody out there has any thoughts or is willing to answer. The reason for this assumption and what this limits or prevents is what? Does anybody have any idea that if you take a straight bar and you apply the load on the centroid of the cross section, what does that mean? Why is that? Why is that significant? Nobody gonna take a shot? Well, maybe I'll rephrase the question this way. Give you one more chance. What if the bar was not straight? What if it was bent or curved and you pulled on each end? Compared to the example we see here where it's straight bar. No thoughts there? The other part of this is it acts at the centroid. What if it was applied out at the edge? What if the force was applied over here along the edge rather than the centroid?
Does it prevent buckling?
No, but at least somebody took a chance. Okay, so I actually got a response here from Dominic, and whether it's significant or not, I don't know. That would depend on the values, the forces, and the dimensions and stuff. But you would have a moment, right? It would cause this thing to bend, right? So that's what this first assumption means, that there's say no bending. Right? If you take a bar that's curved or bent and you pull on it, you're going to have a bending moment. That thing is going to bend. if you apply the load at the edge, it's going to cause the thing to bend. And so you're going to have stress due to the axial force, and you're going to have stress due to bending. And again, we're going to get there. We'll combine those later. But to ensure that we're just looking at stress due to the axial load, this is one of the assumptions that we have to make. All right, the second one deals with the material. We're assuming the material is homogeneous, big word, N, and isotropic. So basically, we're assuming we have the same material properties. Throughout the bar in all directions. So basically, we're assuming this thing's all the same material. We will see to some extent, some of you, depending upon your major and what kind of structures classes you take after this, you're very likely to see lots of examples where you got members that are made of different materials, and that does not behave the same as if it was all the same material. So that's the reason for this assumption. So we're assuming that each of these axially loaded members are all the same material. And again, you would see if you had different materials, you could get bending if you had that. So that's the whole purpose in those assumptions, is to assume that we're not bending the bar. Now, if we kind of do what we did yesterday, if we come in here and say cut this member somewhere, what you would see, my artistic ability is not great, but let's assume this is where we cut it. Right, so we're taking that cross section there where we cut it. Now, what you would actually see, if you could actually cut something like this and look at it, you're not going to see a concentrated force acting on that cross-sectional area. What you would actually see is a distributed load. You're going to see this distributed load. It's going to be acting over that entire cross section. Now, we know from statics, though, that we can replace this distributed load, with an equivalent resultant force. And the result of this, we're going to wind up, is pretty intuitive, but just want to make sure everybody's clear and does understand that in reality, on that cross section, there's not going to be a concentrated force, but we can replace it with an equivalent concentrated force. And so we got this resultant equivalent force from that distributed load. But equilibrium tells me that equivalent resultant force has got to be equal to P, right? So this has got to be equal to P. This is, again, since sum of forces equals 0, well, I've got P acting down. I got to have P acting up. And so the normal force acting on that cross-section has got to be the same as P. Now, I've kind of depicted this distributed load as being nice and uniform. Now, and again, this is something else. In reality, it depends on how far away you are from the end. Now, in reality, if you apply a concentrated force P here, if you pull on the end of this bar, right, if you cut it down here close to that, you're not going to see a nice, evenly distributed load. The force is going to be a lot higher in the middle where the forces apply, and very much smaller out toward the edge. But if you get far enough away from that end, then it will be nice, evenly distributed. And there's something called St. Venant's principle. I think it's actually in your mechanics and materials book. I think over in chapter 4. We might have time to discuss this a little more. Basically, if you are close enough to the end, you can account for that using what we call stress concentration factors. That would be something you might see later in a later course, or if you get out in the real world doing any kind of structural analysis, you'll see it then. But for our purposes, we're always going to assume we're far enough away from the end where that concentrated force is that we're going to assume that we have a nice, evenly distributed load acting over the entire cross section. Okay? All right, so we define, again, our normal force, or normal stress, rather. Our normal stress, which, remember, notation-wise, we use sigma here. So it is that normal or perpendicular. I'm going to run out of room here. Force over the cross-sectional area. Or in formula form, if you like formulas, P over A. Where, again, P is that force that's normal or perpendicular to the cross-sectional area. A is the cross-sectional area. So A would be whatever that cross-sectional area is. Now, the sign convention is, if you remember back earlier, it said we could have tension or compression. So the sign convention we're going to use is real simple. You may have used this same sign convention in statics when you did trusses. Yes, reading the question, the distributed load works the same way as the 2D ones we did in statics. Yes, this is just a three-dimensional, which if you want to call it a pressure, you could call it a pressure. But yeah, it's the same thing. So what we're going to do is for if it's in tension, or if we have what we call tensile stress, we're going to denote that with positive. And if we have a compressive stress, negative. Now, this particular textbook really doesn't emphasize this, but in the real world, this is what's done. If you have a tensile stress, it's going to be positive. If you have a compressive stress, it's going to be denoted with a negative. Now, I have seen a few cases, if you don't like the plus or minus, to me the plus and minus is the simplest thing to do. But I have seen this. You could do T for tension and C for compression. So if you like T and C better than plus or minus, that's fine with me. But it is important to denote if it's a tensile stress or a compressive stress. And reasons being, to some extent, same thing it was in statics when you were looking at trusses. If the member is in compression, then you not only have to worry about the material failing due to the compressive stress, but you would also have to consider the possibility of buckling. That's when members in compression, it buckles, it bubbles out. So that's one reason it's very important to denote or differentiate between tension and compression. Another one, a little bit, I reckon, new that may not have seen or heard before is there are some materials out there that behave differently in tension or compression. Now, most metals, certainly most all steels, if you got a steel bar, the material is going to fail the same stress whether it's tension or compression. It doesn't matter. But when you get to some more, maybe, I don't know the best word, exotic materials, they can have different properties if it's in tension or compression. So that's another reason to differentiate and denote tension or compression. All right, so any questions before we've got time? We're going to work one example today. I think that may be all the time we have, but we certainly have time to do one example where we calculate a normal stress. No other questions? All right, well, let's see if we can do an example then. And there's several examples in the textbook. Again, we're not going to have time to work an example like every possible scenario you might see. So certainly in addition to these examples that we'll work here, certainly I encourage you, look at the examples in the book. There's some good examples. So we are going to hopefully find the normal stress on the cross section. Two places, points J and K. All right, so now let me draw this. It's kind of a strange looking bar. It's got different sizes. We got several different loads applying. So what we have is it's fixed at this end. At the left end, we'll call this A. Then this middle section gets smaller. And then it gets big again. And let's see, we've got several, we'll call this B, C, D. Here at B, we've got a pair of 10 kilonewton forces acting to the left. All right, so just maybe mention here, we said previously one of the assumptions was that the loads were going to be applied or acting at the centroid. And hence that's what you see the pair of 10 kilonewton forces. Obviously, looking at that, there's no way each one of those is acting at the centroid. But if you have a pair of them like that, that's equivalent to putting 120 kilonewton force right in the middle, right? But this is fairly common. You'll see the problems like this in the book. But I just wanted to mention that, bring that up in case somebody was thinking, well, those forces aren't applied at the centroid, but the resultant would be. Right, so if you got those two 10 kilonewton forces, same as 20 applied right in the middle. We've got same thing over here, two 10 kilonewton forces, this time acting to the right. And then out here at the end, another 10 kilonewton force, this time, again, applied right in the center. And we are told point J is right here somewhere in between B and C out there. Doesn't necessarily have to be right in the middle. K is some point here between C and D. And we're told that the area of section BC is 0.000, I think, 3 zeros meters squared. So the cross-sectional area for the section between B and C is given. The cross-sectional area for CD here, that piece of the bar is 0.002 meters squared. Right, and so if you remember to calculate normal stress, that's what we're trying to find. Right, what we've got to have is what's the normal force, and we divide it by the area. Right, so the area is given. And so really the work that we have to do here is to calculate what is that normal axial force acting on the cross section at those 2 points, J and K. Right? So we're going to find that internal normal force just like we did yesterday. Right? So let's do K first. So we're going to look at this section here at K. Right, so we're going to cut this thing. We're going to cut it in half at K and determine what is that normal axial force acting on the cross section at K. Now, this one should be, it's almost simple enough. You should just be able to look at this and tell. But I caution you, be careful doing that. It's always better. Draw the free body diagram because this is where I see the vast majority of mistakes made with problems like this is get the axial force wrong. And most people who do that, they don't draw a free body diagram. They just say the axial force is, 50 and do 50 over the area, and they don't, there's no work. I have no idea where they got that from. And obviously you're going to lose lots of points. So always be on the safe side, draw the free body diagram. Now, if you remember from our previous discussion when we were doing this, we cut it in half. We can work with the left half. We can work with the right half. Now, in this case, I think everybody would agree that there's going to be less work to do if we look at the right side over here, right? Because we could do it this way by looking at the left side. But keep in mind, if we do look at the left side, we got a fixed support over here. And we would have, well, focus for me. Yeah. There we go. This is fixed support. You got support reactions there. Now, 2 of these are 0, just by observation. If you look at this, we don't have any other forces in the y direction. AY is going to be 0. We're following our assumptions. All of our forces are, along the centroidal axis. We're not bending this thing anywhere or causing any moment. So the moment would be 0. But AX is not 0. So we would have to calculate AX. Plus, we got a lot more stuff over here to deal with. So it just makes sense if we're going to cut it to use the right side, right? We don't have to find any support reactions. And there's not a whole lot over here, right? We've got, here's K, right? So that's where we cut it. So we've got a 10 kilonewton force acting to the left, and what we're trying to find is what is this axial force P that's acting on the cross section there at K. And I hope everybody could tell me that just by looking at it. But if you can't, if you need to write down the equilibrium equation, again, it's always safer to write it down, get it right, than to do it in your head and get it wrong. So if we take, let's say positive to the right, We've got minus PK, we got minus 10 equals 0. So that axial force PK is going to be minus 10 kilonewtons. Right? It's in compression. Right? It's in compression. Now, one other thing maybe to point out before we calculate the stress here, going back to what we did yesterday, you could assume this force, axial force, is going whichever direction you want. We could assume it was going to the right. We would have got PK here is positive. But I intentionally assumed it was going this direction for a reason. Again, this goes back to, I don't know when you took statics, when you did trusses, but I know when I teach statics and trusses, I tell my class to assume tension. And that's what I'm going to recommend here. So assume tension here as far as the direction goes. The motivation, reason for doing that is the signs take care of tension and compression for you. If you assume tension, then if you get a positive, that means it's in tension. You got tensile stress. If your force comes out negative, it means you got compression. You got a compressive force. So if you assume tension, the signs take care of themselves, right? You don't have to keep up with, is this tension or compression? Plus and minus does that for you, right? So that's the motivation there. All right, any question how we got our axial force P acting here at the cross-section K? All right, so let's calculate the stress. We won't get the normal stress there at K. We just take what that axial force is and divide by the cross-sectional area there. Well, we calculated that force was, again, 10 kilonewtons. And again, I'm going to use plus or minus for tension and compression. So this would be minus. And it's kilonewtons, so I'm going to go ahead and convert it into newtons. So that'd be minus 10,000 newtons. Our area was given, K here is section CD. This is 0.002. And so we're going to get a negative, very large number, 5 million. I think I got the right number, 0. Again, these are newtons per meter square. That's a Pascal. So that would be the normal stress acting on the cross section at K, minus 5 million pascals. Right? It's in compression. Now here's where, if you don't like writing out big numbers, right, this would be minus 5 megapascals. That's the way you would most likely see most real engineers out there in the real world would write it as megapascals rather than 5 million pascals. And again, the negative is indicating it's in compression. Now, I said a minute ago, if you don't like the plus or minus, you could also write it as 5 megapascals in compression. That would also be okay. So this is good, this is good. If you want to do both, that's okay too. If you wrote it as minus 5 megapascals and put a C out there, that's good too. That never hurts to over communicate. But somehow or another, you've got to indicate that this is compression. Now, if you just told me the answer was 5 megapascals, that I'm taking points off, because when I see 5 megapascals like that, I'm interpreting that as tensile stress and tension, and it's not. It's in compression. All right? Everybody clear about notation-wise how to indicate tension or compression? Any question about how we got the stress? All right, well then we got one more to do and we'll be done. All right, we're going to basically do the exact same thing. All right, this time we're going to cut it through J. And again, we got to look at the free body diagram to the left, or we look at the free body diagram to the right. Now here it's right in the middle, but still, unless you want to calculate what AX is, let's go stick with the right side. And let me emphasize, when you cut a member like this, when you draw the free body diagram, say we can cut it here. We're going to draw everything to the right of that point, or everything to the left. We can't just take a little piece in the middle. It doesn't work that way. But I see students do that all the time. Like here, if we cut it at J, we got to do everything to the right of J, or everything to the left. We can't just look at this little piece in the middle. If we draw that, it doesn't make any sense, and we're going to get the wrong answer. All right, so let's stick with the right side. So here's J. That's where we cut it. And we've got our two 10 kilonewton forces going to the right. Again, this is C, this is D. We got 10 kilonewtons here going to the left. And we want to find what is this. This is J. What is the axial force acting there at J? Again, I'm assuming tension, so that way my plus or minus will correspond to tension and compression. But notice I've drawn everything to the right of where we cut it. Right? We can't just look at a little piece here. And like I said a minute ago, we got the two 10 kilonewtons. That's the same thing as putting 20 right there in the middle. So when we sum forces here, we've got P, I assume, is going to the left. We got 20 going to the right, and we got 10 going to the left. So if I'm looking at this right, almost made a mistake. All right, we took positive to the right. I forgot my minus sign. P's going to the left. So when we solve for P here, it's going to be positive 10 kilonewtons. Right? It's positive. This thing's in tension. Right? So you go back to the original bar up here. This is kind of strange situations that can arise. CD, that section's in compression. This middle piece, BC, is actually in tension. But now we have the axial force. We're going to get the stress the same exact way. Take that axial force, divide by the cross-sectional area. So we've got 10,000 newtons. The area, we go back up here, and BC, cross-sectional area is 0.003. And that comes out to be, it's like 33.33 times 10 to the 6 pascals. Or how most people would write that is 33.33 megapascals. Right? But it's in tension because the axial force in that section is in tension. It's pulling and stretching it. And so just kind of a sneak peek ahead, we're going to, when we get to a little more talking about the material side, depend upon what this material is, we could look up its property and see, is that stress too big, right? Is it going to cause this thing to break? It could. It depends on the material, what the failure stress is for that particular material. But we got to be able to calculate the stress before we start talking about the material. If you notice, this is all statics, except for, this is the only mechanics of materials part of the whole problem, is knowing that normal stress is the axial force over cross-sectional area. You do statics to calculate that axial force, and you plug in those formulas to get the stress, right? So there's one example. We'll do one more example maybe tomorrow before we move on to talking about shear stress. So we'll wrap up with, again, any questions you might have on this particular example or anything related to normal stress.
I was wondering if you could just paper up just a little bit.
I can barely hear you.
I was wondering if you could scoot the paper up a little bit.
This way?
Yes, sir.
Okay.
Thank you.
Is that good enough?
Yes, sir.
And I got a question on chat asking, should it be 3.33? But I'm pretty sure, I don't have my calculator with me. My battery died in my calculator. But if you take 10,000 and divide by, oh, that's because I left out a zero. Good catch. The area here is 3 zeros, and I just wrote 2 here. So, yes, if you divide 10,000 by 0.003, yes, it would be right. But where I messed up was I just wrote the area down wrong. So if the area is 0.0003, that gives you the 33. All right.
I have a question. It isn't about the material, but I was wondering if you've decided when the first test is going to be.
It'll be, I can't tell you exactly because it depends on what happens between now and then. Like, depending upon how many more days we have, like yesterday where WebEx didn't work.
Okay.
But approximately, I was looking at about 2 weeks, maybe so I'm looking at the calendar here, probably somewhere around the 15th, the first of that week. It won't be next week. Probably, again, Monday or Tuesday of that following week, somewhere around 15th, 16th, be my best guess right now.
Okay. Thank you.
You're welcome. See, it doesn't kill you for everybody to ask questions. Any other questions? Anything else? All right. Well, then I will stop recording and exit out. Unless, again, if somebody has something you want to stay around after I stop recording.
Hey, can you show me the statics on number 4 of the homework?
I can. Give me just a minute to stop recording, and I'll dig out the book, and I'll be glad to look at that.
Okay.
Okay.
Yep.
All right. So I'm gonna stop recording, and again, anybody else that wants to stick around, you can do so. Otherwise, won't see you maybe necessarily, but maybe I'll hear you tomorrow morning at 11.